Hi, I'm Kian, and in this video, I'm going to show you a high school chemistry version of proving the ideal gas law. So if you've taken chemistry or physics, you've probably heard of the ideal gas law. Um, and in many labs in chemistry and even sometimes physics, you do certain experiments to show the relationship between four different things: pressure, or volume, temperature, and amount of gas. And let's say we have done those experiments, and if you um, know what those experiment results are, it's actually that pressure is proportional to um, to the inverse of the volume, or it's proportional to 1 over volume. So we can say that P is proportional to 1 over volume. This means that if P increases, pressure increases, the volume decreases, and if volume decreases, pressure increases. We can also find out that by common sense that pressure and temperature are proportional. So if we heat something up, the molecules of gas exert more pressure. So it means that exert more force in a certain area, because pressure is basically force over area. So we can say that pressure is proportional to temperature. And in this case, we assume that the volume is constant, because in the next example, we know that volume and temperature are also proportional. And so in both of these last two cases, um, pressure and volume either have to be constant, because we know that pressure and volume, they are separately inversely proportional, which means one increases, the other decreases. So for example, here, if temperature rises, assuming that the volume is constant, then the pressure increases. For the third one, if the temperature increases, the molecular collision increases, so it speeds up. It means as they bounce off each other, so it expands. But again, we're assuming that the pressure is constant. And one more is basically the proportionality of volume to the amount of gas, which in chemistry is denoted by small n. And we know that if, for example, we add certain amounts of gas into kind of a container, assuming that the pressure is conserved and it hasn't changed, basically, we can conclude that the volume also increases. And then lastly, we also have one more, basically the relationship between pressure and amount. So again, if we consider the volume to be constant, then if we increase the amount of gas, kind of this is all the case of an ideal gas for all of these. If we increase the amount of gas, then the pressure should also increase. So these are all kind of proportional relationship between these four variables. And so we want to make an equation from it. So let's say our teacher says, so form an equation that kind of shows all these relationships. So I'm going to show you how. So basically, we're starting with the first one. So we know that generally, and it's also proved, if you want to check out, it's proved by Boyle's law, that pressure and volume are inversely proportional. So if we have such a kind of relationship, then we know that, for example, we can have our equation in terms of P equaling something, we don't know what, but over volume. This is a famous case for showing inversely relationship. It means that if volume increases, this means that the denominator increases, so the pressure decreases. But if volume decreases, then the denominator decreases, so pressure will increase. But now what should we have at the top? Since we know that pressure is proportional with temperature, with temperature and N, which is number of gas, we know that off the bat, we know that on the top, we should have temperature and number of gas, or amount of gas, N. So in this case, if we increase one, again, assuming that the volume in this case is constant, the other increases. But a better way of writing this, so we can show kind of all of these relationship, is PV is equal to Tn, or temperature times the amount of gas. So in this case, we're showing how if pressure increases, the volume also has to decrease. And the fact that both pressure and volume are proportional to temperature and the amount of gas, considering either one to be constant. So if we kind of emit pressure to be constant, then temperature and amount of gas are proportional to volume, and vice versa for pressure. Now, basically, for checking an equation or an identity or a rule to be true, both sides have to have the same unit. So let's check. If we check the units for each. So I'm going to start with the right-hand side. I'm going to use a different color, maybe green. For the left-hand side, I'm sorry. I'm going to write pressure as its usual force over area. So we're going to write this as force over area. Over area. And we're multiplying it by volume. So this is being multiplied by V. But we know that volume is basically an area times a length. For example, if we want to find the volume of a cube, we basically find the area of one of the faces, or the square, for example, face, times the length. We do that for every shape. So basically, we can write this technically as force times length. And that length is basically the distance. It's kind of the horizontal or vertical, but it's not kind of a height, it's kind of a length. So I'm going to just kind of generalize the length as distance. So force times distance. But what do we physics lovers know about force times distance? Force times distance is in fact work. So work done is in fact the force exerted times the distance that it has traveled. And in fact, this is precisely equal to work, which is denoted by W. And if you know kind of physics, work is in joules. Joules. Now we know that the right-hand side should equal joule. Now, if you know about ideal gases and how they work technically, we use Kelvin for temperature. And the reason is because for gases, they behave differently as liquids. So we can't technically use Celsius because, for example, a liquid has a freezing point at kind of 0 degrees Celsius. But for gases, it's different. We can have temperatures of 0 degrees Celsius, but if we use 0, then we get into, if we use Celsius, we get into values of 0 and negative, which we can't technically have in kind of ideal gas and solving for pressure and volume. So we use a better kind of version, which is Kelvin. So the unit for temperature is in this case Kelvin. So I'm going to write it as capital K, and there's no degree symbol. And unit for N, again, if you have taken chemistry, is in moles. So is in fact in moles. So then now we can see a clear distinction between the two sides. One side is in joules, one side is in Kelvin times moles. So we know that if we have a constant, which we should have because the product are not equal, we can't really simplify either of them more as they are. Joules is a more simplified case. We can't really simplify Kelvin times mole, which means that our constant, which we call, let's say, question mark, let's say we call this constant, should be joules, which I'm going to call it J, over Kelvin times mole. I'm sorry if I write it should be capital K. Capital K times mole. And the reason is because when we multiply that constant by temperature and amount of gas, the Kelvin and mole cancel out, and we're left off with joules. And now we basically proved this. Now, the person who may kind of identified this ideal gas law called this constant R. And in fact, if you learn the ideal gas law, this constant is called R, which is where the ideal gas law comes from. So we've just proved that, or shown that, that PV is in fact equal to nRT. And this has, the ideal gas law has two ways of writing. You can also use another version, which is basically The constant is different. The constant is Boltzmann constant. You can check it out if you search. But basically, both are similar because both kind of their units is different for the constant, but both kind of produce joules as it's in the left hand side. Thanks for watching. I hope you enjoyed it, and bye.